right. Get a couple more here.
All right. In theory, we are live. We did it.
Did it.
Yeah. Hey, everyone. Thanks for joining me on this open space for Monday, April the 6th, 2020. Time has no meaning anymore. Joining me today, a return visit from Professor Brian Keating. Brian, welcome back to Open
Yeah.
Space.
Thanks, Fraser. I think I was on exactly a year ago today or tomorrow or
Yeah,
yesterday.
and we were talking about, I don't know, something about cosmological, bicep 2, primordial
That's
gravitational
right.
waves, etc.
Yeah, my
And
book had just come out
yeah.
in paperback. Yeah, exactly.
So
Good to be
first,
back.
you're in California, right?
I am. We are in California. I'm not in a hot zone, thank goodness. But
Yeah.
we are shut down on lockdown or shelter in place, as
Yep.
my boss slash the Governor Newsom tells me.
Yeah. Well,
Stay in place. So
I mean, we're in a similar state here in Canada and have been now for about 3 weeks or so, probably closer to a month now at this point. And we can definitely see the curve flattening here in Canada, which is nice. It's still, we're seeing about the same number of cases every week at this point, and the deaths are still fairly low, which is nice. I know it's kind of scary in the U.S., and I really hope that you guys will see this break as
yeah,
soon as possible and
I
get
think
back.
it's.
Part of like just when can we go back to work, right? When can
I know.
when can the
Yeah.
economies start back up again? Because if you get the timing wrong, then you got to go through the whole thing all over again.
Oh yeah. I mean, for me especially, I've got kids, young kids at home,
Yep.
got graduate students at school, and I'm just trying not to, teach toilet training to my graduate students and
Getting,
quantum mechanics to my 2-year-old. I don't know.
yeah, you got to keep it organized. I'm also finding, even though I, in theory, should have a lot more time now because I'm like at home, and yet I still am not getting all the things done that I wanted to do. So now maybe it's me. Maybe it's not that I
Yeah,
never had enough
exactly.
time, but
It's not you.
it.
It's me. Yeah.
Yeah, exactly. So for people who missed, I guess our last conversation, who are you and what do you do?
So I am a professor of physics at the University of California at San Diego, the southernmost UC school until we open a branch in Tijuana, which could happen someday. Nothing is beyond the imagination at this point. Speaking of imagination, I'm also the co-director, the associate director of the Arthur C. Clarke Center for Human Imagination, which also runs a podcast, and we have about the logarithm of your number of subscribers. So we're working our way up the curve of the
Perfect.
universe today.
Yeah,
But
well, we've seen exponential growth is a powerful thing.
yeah, exactly. I'm hoping to tap into to some of that R naught that you give off.
Yeah.
And I am also the author of a book called "Losing a Nobel Prize," a story of cosmology, ambition, and the perils of science's highest honor. And now in paperback, audiobook, wherever you get books, you can find it. And the book really is sort of a memoir of what it's like to be a scientist, the young scientist, pursuing what became somewhat of an idol for me, as it is for some other scientists that I know, which is the Nobel Prize, and how that affected and afflicted my mentality, and ultimately came out the other side with kind of a renewed vigor for the type of science, which is cosmology, that I'm privileged to do.
So, I mean, it's been a year, and so, I mean, if people want to sort of go through all of the details of that story, definitely go back. I'll put a link in the show notes so people can go and see the previous conversation that we had, just about this process of feeling like you had an incredible discovery by the tail, and it ended up being not what you thought it was, and what that process felt like, and watching it unfold. And it was I thought a fascinating journey through what it must feel like for all of these scientists who are pushing the boundaries, and only some of them will be right, and only some of those will actually end up with that high, that highest accolade, which is the Nobel Prize.
That's right.
And so, fascinating story. I greatly enjoyed the book, and I also really enjoyed a lot of the recommendations that you had for how to improve the whole process. But I think that, what I think is really interesting is that there have been a ton of changes in the field of cosmology, or a ton of new issues pop up or really reveal themselves in the last year since we talked. And this is right in your wheelhouse. So let's talk about this.
Yeah, so what cosmology purports to do, for your listeners who may not be familiar, is to approach the origin and evolution of the universe on really three fronts. One is through theories, new theories of cosmogenesis. How did the universe originate? Another avenue, and that's, it could be pencil and paper. It could be by mere thought experiments, as folks like Lemaitre, Galileo, going back as far as Galileo and beyond even, have pondered how did the universe come to take on the appearance that it does. Then there are the observers, those that use telescopes, like the one behind you, and the ones that we use, although they don't use optical wavelength light, we use microwave radiation to unravel the properties of these very wispy photons that themselves have been proven to have an origin a few minutes after the formation of the first elements, hydrogen and helium, really. And then there are people that build experiments, and there are people that use telescopes. And I'm in the former camp. I build telescopes. And one of the telescopes I designed and built, along with colleagues from all over the world, was called BICEP and BICEP 2. And that's the main character, the protagonist in losing the Nobel Prize, is BICEP 2, which is shown here at the very bottom of the world, Antarctica, where I've been there twice. It's quite a journey to get there, and even more treacherous than the weather we're currently having here in San Diego. And then there are people that
San Diego weather, I can't even imagine. Brutal. Yeah,
I know. I always say the hardest job in the world is being a San Diego sportscaster, because we've never won a championship in any sport, major league sport. But the easiest job is usually being a meteorologist here. But today it's a little bit.
It's going to be perfect showery. Again.
Exactly. Yeah. 72 and sunny with a slight breeze. But the third kind of branch of cosmology revolves around using data, and really it's become intensive in a way that the founders of cosmology, which would plot like Hubble, and we'll talk about the Hubble constant, the Hubble controversy. When Edwin Hubble published his famous, sort of Hubble diagram, which showed the evolution of redshift with distance, so the recessional velocity of galaxies, the farther away they were from us, the faster they were receding. He had 30 points on his data plot. We're talking about, with my new project, the Simons Observatory, collecting a terabyte of data a year. So you're talking about hundreds and hundreds of gigabytes on a regular basis. And a terabyte, close to a petabyte. Terabyte would be easy.
Yeah.
We're talking about a petabyte. And that's getting into the realm of high energy particle colliders and things like that, when you have to analyze that data.
Or the Vera Rubin Observatory.
That's Vera Rubin Observatory, yeah.
Dumping that kind of data.
And so, exactly. So these are massive data sets that cosmologists could hardly have dreamt about years ago. So really, experiment theory and observation using massive data sets have become the norm in my field.
And so, the age of the universe, this idea of the Hubble constant is something that astronomers have been attempting to calculate for a long time. And they thought they had a pretty easy concept of it. Measure how fast the universe is expanding today, run the clock backward. That tells you how old the universe is. But it turns out that we have two answers for the age of the universe, both of which are accurate within their error bars and both of which disagree with each other. How has it been to be sort of in the middle of this and watch this unfold?
Yeah, this is one of the most exciting developments in many years in my field. It's a welcome change from having, the Chinese have a proverb, may you live in interesting times, but, you don't have to be too interesting. Take it from me. When you have a really controversial result like we did with BICEP, there's only so long you can maintain that level of intensity. So it's nice to be kind of a peripheral visitor on this field of controversy that's now swept up colleagues of mine, both in classical observational astronomy, folks like Adam Rees at Space Telescope Science Institute, and then folks in the Planck CMB satellite team, not my project, collaborators, friends of mine that work on that. And they both get two results, as you said, that differ by about 9%. And 9%, that doesn't sound so bad. But each one claims a precision about their results that, we have these you have to think about these two kind of bell-shaped curves, and their central points differ by 9%, but their overlap says that the probability of that happening is 1 in what we call 5 sigma. So it's a 5 sigma discrepancy to occur by fluke, and that's something like a 1 in 100,000 chance of getting it wrong. So a 10 to the minus 4 in percent units, or something like that, a few times that.
Right.
And so the question of how these two teams, which have had extensive analyses done both by them and by their competitors, could be so radically far off as to require a fluke fluctuation of 1 part in 10 to the 5th or better. It's just astounding. And so the ways that these are observed and the methodologies used are completely different, which sounds kind of like, well, why would you expect them to agree? But it's kind of like this. I have a bunch of kids, as you know, but the oldest one, he's now 9. When he was 2, we took him to the doctor for a checkup. The doctor did all that, weighed him, did this, and he measured his height. And he said, according to this, he'll be 6'3" when he grows up. I said, I better beat him up a lot now because he's going to be a lot taller than I am. I'm only about 5'11". But they used his current height and a statistical prediction, a model, to forecast in the future how tall will he be. Now, this doctor will probably be long retired or worse, maybe, by the time this comes true or does not. But you can use a model and statistical sample that has a very high numerical precision to get an accurate forecast of how tall a child will be. Which boys, girls, whatever. And this is just the rule of thumb that they use. For cosmologists, what we did is we take a snapshot of the early universe using microwaves, using the cosmic microwave background radiation, in this case done by the Planck satellite. But the results agree with the WMAP satellite, which was the predecessor by almost a decade. And you forecast the expansion rate of the universe and how fast the universe will be expanding in the future. And there's only a few terms in this equation known as the Friedmann equation. And that can tell you everything about what the present day universe should look like according to the models and predictions of the pristine early universe. Likewise, you can take data from supernovae today, what are called Cepheid variable stars, things in the local universe, as you would say, the universe today, more or less. You would take those objects, extrapolate back, and they just disagree wildly. Question is, how can that happen? And so part of the fun of being a cosmologist is when you have these controversies, as long as there's not a blunder, a mistake, a wrong interpretation, which is what we did with Bicep 2. We didn't make a blunder. We didn't leave the lens cap on. We didn't have a thumbprint on we detected something with exquisite precision. In our case, dust. In the interstellar
dust.
medium. Dust. And I think that dust is going to come out. There's a meme that goes around on Twitter, and you can see it when they test medications. Even now for COVID-19, they're testing hydrochloroquine or whatever, and they're testing, and they'll say that has great efficacy, proven to be, and it says in little print, in mice. And so there's a meme on the internet called "Just Say Mice," and I feel like we should have one for astronomy. Is just say dust. Because everything from Oumuamua to the dimming of Betelgeuse to the origin of the universe via inflation,
Tabby's star
has to. We did
a whole episode on this, on dust, and just went through thing after thing that has turned out to be dust.
Yeah. Oh, that's fascinating. I wrote a couple of pieces for Astronomy magazine, and for Bill Gates runs this wonderful site called the Big History Project, or set it up, and I wrote an article for them for high school teachers. And it's really amazing how dust. And it's fitting we're talking on this day. This is the day after we received the sad news that my colleague, Margaret Burbidge, had passed away. Maybe we'll get into it. She was known as Lady Stardust, and her observations really led to the solidification of the current cosmological model that we know and love today.
So what are the? I mean, let's assume that the Planck, there are no major mistakes, as you say. The Planck data is very accurate. The more modern measurements of the Cepheid variables of the Type 1a supernova, those are all accurate. What are the possible reasons why you've got this discrepancy between, your son's 2-year-old version and the 6'3" man that he's going to become?
A strapping hunk of a man. So there are many different ways to get out of this, and everyone sort of has their own preference for how you do it in the theoretical community. And for my money, I am still sort of banking. Maybe it's not dust, but maybe it's some unknown systematic effect. And the systematic effect is kind of like the butcher's hand on the scale or whatever, that kind of makes an offset to the measurement you're trying to unravel. And the only way to get at a systematic effect is to do a measurement that's completely orthogonal, that uses completely different technology, techniques, tools than the ones that are used previously. And part of that is going to be possible with the advent of new observatories, such as the LIGO Observatory. We can get into that, how that could come about in a minute. But the main way that we think we could resolve it without resorting to a model that's exotic, such as new forms of matter, new forms of energy, might just be something as simple as a systematic effect that's not accounted for in the early universe, or one that's not treated in the late universe. And Adam Rees and his team are well versed in this, especially when it comes to things like dust, because that bedevils their measurements ever since they started taking them in the 1990s. That led to our understanding of the acceleration of the universe that we know and love today.
So let's take those apart one by one then. So the orthogonal method of measurement, you mentioned LIGO. LIGO might not be the machine that can do it, but there are other really powerful gravitational wave observatories in the works, LISA, the Big Bang Observatory, and others, which may get at directly measuring those primordial gravitational waves, which you had attempted your bank shot to get at them. This may see them directly. Would that resolve it right there and then? Like, if you could just look at the gravitational wave data, would that tell you everything you need to know?
Well, it wouldn't necessarily tell us everything we need to know, because, as I said, when you have two different measurement types and they agree or they don't agree, that's powerful evidence or powerful inclination that something's wrong or something needs to be understood that's not currently well understood. In our case, what the new measurements would result, they would provide a local window, which would really be so I should take a step back. How are they measuring the distance scale in the early universe? It's very easy to measure redshift. Redshift is the recessional velocity that's attributable to the motion of a source. And it could be motion, proper motion, like the Andromeda galaxy is coming towards the Milky Way galaxy at a certain speed because we're gravitationally attracted to one another. However, once you get beyond several times the distance to Andromeda, you get caught up in what's called the Hubble flow, which is the actual expansion of the universe, which, as Rees and Perlmutter and Schmidt's group showed many years ago, is accelerating. Let's not get into that. So you measure the redshift. It's very easy. You take a spectral measurement, you compare it with the rest frame spectral measurement of, say, the same element, hydrogen. Glowing hydrogen emits some number of characteristic spectral lines, depending on its electron configuration. You compare that to this one, and just like an ambulance moving away from you at great speed, the pitch will be reduced because this thing is moving away. In our case, the red will be the wavelengths that are characteristically shifted towards lower or redder frequencies or wavelengths. In the case of the Big Bang measurements using the CMB, we don't do that. We're not looking for the expansion of the cosmic microwave background. So it's a little bit harder to know the actual redshift. Instead, we sort of assume things about it. But what the microwave background depends on is what's called is sort of called a standard ruler. So we know that there's a characteristic scale in the sky, and you know that these paperbacks come in 8 to 9 inches long and so forth. And so the farther away I move from you, you can measure the length scale, and it will appear to be smaller. And that could be used as a very, very difficult to use ruler, right?
Right.
On the other hand, if I have this light bulb on my iPhone, I move it away, it gets dimmer. That's the type of measurement that Rees and collaborators are doing. They're doing a luminosity, a standard candle. So there's a standard candle that the optical astronomers are using. There's a standard ruler that the cosmologists are using. And what LIGO is going to use is called a standard siren. So if you know the properties of two black holes, Einstein's relativity tells you their in-spiral rate. And that could be used directly to produce a frequency, another kind of frequency, which should also redshift with distance.
Right.
So that's a standard siren.
So it's
now you'll
not
have three
just
things.
Right. So it's not just about being able to see the primordial gravitational waves. You literally, if you can find black holes spinning around each other anywhere out into the universe, you should theoretically be able to run these calculations and know how far away they are and calculate that expansion of the universe.
And that's what makes LIGO so interesting. Exactly.
Right, right, right. And so we don't necessarily need to wait for those super fancy, futuristic, incredible
No.
telescopes. Just a better version of LIGO, maybe. I don't know if
Or
you
more
heard, like just
data.
like today or the last couple of days, they detected two white dwarfs
Oh,
in
yeah.
orbit around each other,
Yeah.
not collided with
Right.
LIGO, which is
Yeah.
so just find
That's
that
another
in
kind of
another.
siren. Yep.
Yeah, and so find that in another
Yeah.
galaxy, and you're set. Um,
Exactly. Yep.
Okay, so we talked about this idea of using this other or orthogonal, this other method, gravitational waves, to really, like, that is like the most useful thing that could come along. But until then it's a mistake.
Yeah.
So where is the, and I just want to take a second as well and just really note, right, that you are excited. Like, and
Yes.
this has been the response from all the cosmologists and astronomers I've talked to. Nobody is grumpy that this is sort of that there is this controversy going on. Everyone is stoked to
Yeah.
solve it.
We have full employment for decades to come.
Yeah, but just like, this is the point, right? That science
Yeah.
loves these kinds of mysteries, and
Yeah,
that's what,
scientists are children at heart.
yeah,
And what do children like to do? They like to play with toys. They like to solve puzzles. If they like to do, I see some things with my 2-year-old twins. They'll do something, they'll figure out how to solve some little, baby puzzle with 5 pieces, and they'll have the same excitement as when my 9-year-old solves a Rubik's Cube, or when I finally understand this equation or code that I've been working on, or get this instrument to work after long hours in the laboratory. So the key is to maintain that childlike passion, that enthusiasm, without the pettiness that children also have, which is jealousy and
right,
envy and so forth. And
yes.
scientists have that in abundance as well, as you
That
know.
is true. Yeah. So I'm, we're rabbit holing here. Please, what are the sources that we can try to figure out that might tell us what's going on here? What are the,
So those three are interesting because they're orthogonal in a sense. They intersect at right angles to each other in a complex parameter space. There are other versions of those techniques. Like you said, the white dwarfs could be something in a distant galaxy, but that would be a different example of a standard siren. There could be other, supernovae or novae that could be used. There's gravitational lensing, which is an effect that causes a time delay as things pass through a lens. If this was a clear bottle, I'm looking if I have a clear bottle here. I just have my chewy mug here. But as light goes past a massive object, it gets deflected gravitationally. And depending on the angle and the geometry, it can take longer or shorter around the left side of the galaxy or the right side of the galaxy. And that time delay can be related to the distance away the source is. So that's a fourth way. There's also something called baryon acoustic oscillations. These are measured by the Sloan Digital Sky Survey and other surveys, and they'll be very well measured when something like the Dark Energy Survey instrument goes online and other instruments like it. Those are more similar to measuring the sound speed in the early universe, except they're measuring the sound speed in the late time universe when galaxies themselves formed. So it's a similar type of technique, but on a much different age epoch of the universe. And I should take one last step back before, out of the rabbit hole, and just say, why is the Hubble constant so important in all of this? Well, it turns out, you may have noticed, people listening and watching, that the universe, when describing its expansion rate, uses the Hubble constant. And this is first parameterized by Edwin Hubble himself, and it relates the distance to an object to its recessional velocity. And its recessional velocity, once you get far beyond the local grasp of gravity of our Milky Way galaxy, can be indicated by just a simple measurement of redshift, which again is easy to measure, but distance is really hard to measure. At any rate, the units of this strange thing relate velocity to distance. And so it's the only way that it can have that is if it has units of time. The actual units used are called kilometers per megaparsec, so kilometers per second per megaparsec. So you have such and such kilometers per second per megaparsec. That means a galaxy is expanding away at 70 kilometers per second if it's 1 megaparsec away. If you could get out of the Hubble into the Hubble flow, that means if you're 2 megaparsecs away, you'll be expanding at 140 kilometers per second. etc. But if you do a quick bit of math, you'll notice kilometers are units of distance. Megaparsec, despite the Kessel Run from the famous movie Star Wars,
Yeah.
The Kessel Run was incorrectly denominated in parsecs using time, but actually parsec's the unit of distance. It's related to a light year, which is the distance light travels in 1 year. So therefore, you have kilometers divided by distance. You could also express parsecs in kilometers if you wanted. So you have, what drops out are distance, and you're left with 1 over time. So if you take that and you divide 1 into that number, you get something that's in seconds. If you convert the number 70 kilometers per second per megaparsec, I urge all homeschool students out there to do that.
Yeah.
And you convert it to seconds and then divide by 31 million seconds per year, you'll get a number that's about 14 billion years old.
Right.
And if you change that, Fraser, as you know, if you reduce that to the level measured by the CMB satellites like Planck, you'll get something that's 10% smaller. That means you'll get an age that's 10% older, which means that you're talking about 1.4 billion years difference between these two things. And each one says, I agree, to the percent level of precision. It's just fascinating. And that's why you see, I get excited, my colleagues get excited, and we're going to be building new and measuring more and more properties using the CMB, using ground-based instruments such as the Simons Observatory.
Right. Now let's assume that the reason for the discrepancy comes down to dust, like it always does, and it's just a matter of figuring out how and where the dust is confusing the system. But let's say, so throwing dust aside, what is the reason for the discrepancy that you find most compelling? That if you could investigate one as far as down the rabbit hole as you could go, which one would it be?
Well, so this is always the problem, right, Fraser? You don't want to ever say what you prefer, what you're betting on, what you're banking on as a scientist, because then you let emotion kind of get into your mindset.
But where would you start?
Where would I start?
Yeah.
So in the cosmology area, what will be required? We can't make measurements much better than the Planck satellite, because the Planck satellite was in orbit using temperature.
Yeah.
So Planck measured this temperature pattern of the microwave background with exquisite precision and angular resolution. Did it better than the WMAP satellite, and it agrees with the WMAP satellite. There are some subtle differences. If you divide the sky up in certain ways, you'll find anomalies that are hard to explain. But ignoring that and ignoring how they processed it, if you take it at face value, you're stuck, because you can't do any better using the temperature of the microwave background.
Yeah.
But we have another tool in our toolkit, and that's called the polarization of the microwave background, which is what I study. And polarization of light tells you about the interaction between light and matter. In my case, my primary job is to see how could waves of gravity in the early universe have perturbed the distribution of matter to make it uneven in a certain way, producing what are called B modes, or a certain type of curling, twisting pattern of microwaves.
And I'm kind of imagining, sorry, just to tell people out here, I'm sort of imagining you've got those black holes that are spinning around each other, and maybe they are surrounded by some accretion disk of dust. And as the gravitational waves are propagating outward from those black holes, they're causing literally space in itself to, expand and contract.
Yeah,
and it would leave some kind of telltale signature in this accretion disk as these black holes are whirling around each other, that you could then look, if you couldn't see the black holes, but you could just see this accretion disk, you would have a sense of what's going on in what the black holes are doing by what you're seeing from the ripples, from the impact of the gravitational waves. Is that the gist of it?
Yeah, that's right. We're not looking for waves of gravity from merely the in-spiral of a 30 mass, as enormous that is, to 30 mass solar mass black holes. Instead, we're looking at all the matter in the universe. And instead of looking at it, kind of accreting in the last millisecond, we're looking at a trillionth of a trillionth of a trillionth of a second. So the sort of gravitational wave energy that's produced is more or less proportional to the amount of matter that's being accelerated and the time scale over which it's being accelerated. In the case of waves of gravity from compact objects, you can roughly think about the same kind of thing happening in the early universe. But what we're looking for is a crisp test that rules out or confirms aspects of two radically different cosmological models. One that presupposes there was an extraordinary rapid expansion of the early universe. That's called inflation. popularized by Alan Guth, Andre Linde, Paul Steinhardt in the 1980s. And this theory is seductive because it seems to explain almost everything we see about the universe in its large-scale form, at least, except it can't be proven in a sense. It hasn't been proven in a sense because we haven't detected the sine qua non, the essence of what this model predicts, which are called waves of gravity, gravitational waves. And those would be indicative. We thought we did, and hence the title of the book is a spoiler.
Yeah.
We lost the Nobel Prize, so it didn't really pan out the way I hoped.
It turned out to be dust.
But then one of the three gentlemen I just mentioned, Paul Steinhardt, he kind of started to deny paternity, if you will. Later in the early 2000s, he started to worry about how successful inflation was, in a sense, that it could do something that no other theory of science could do, which was that it could produce almost unavoidably an infinite amount of universes. So it could produce what's called a multiverse. Mm-hmm. And the multiverse has a lot of challenges, one of which is that you can perhaps have an infinite number of conversations like this, except your podcast is called Today's Universe, and I'm the host of it. And so looking at how the universe could actually evolve and change with time, it's quite interesting to think about. But for him, it gave him great trepidation because he was afraid that, and he still is, because he no longer believes in the child that he sired, namely inflation. And in fact, he's come up with an alternative model for the cosmogenesis event, which he claims is no more of an event than, say, an infinite series of swings of a child's swing, a pendulum, something like that. And that's called the ekpyrotic or bouncing model. And they couldn't be more diametrically opposed.
Does the bouncing model provide other tests that might be easier to find?
So that's a very good question. That's something I press him on quite frequently, which is exactly.
Can we test it now? Because you're an observer, right? You're an experimenter.
Yeah, so we build instruments. I build instruments, and I'm leading this group of 300 scientists. I'm the director of what's called the Simons Observatory. I'll put maybe a link to the website in your description. And this observatory is going to be comprised of three massive telescopes. One that's 6 meters in diameter, that has a primary mirror and a secondary mirror that are basically the same size, and that's called the Large Aperture Telescope. And then three refracting telescopes, not unlike the BICEP 2 instrument that is the main character of my book. And by using this kind of compound approach, this dual approach of reflecting, refracting telescopes, we're able to both measure the universe at its most delicate, finest scales that could reveal properties of the Hubble expansion using the universe's polarization. And we can look for waves of gravity in the form of these B modes, these cosmic microwave background B modes, that would be the harbinger of inflation. So you ask, are there things that it predicts, this alternative model? Actually, it does not. It currently does not predict anything to distinguish it from inflation, except for one thing. It predicts there should be absolutely no B modes. In other words, it's making a test. It's making a prediction for how you could prove it wrong.
Right.
Whereas inflation cannot be really falsified because no observation can say conclusively, if I never observe it, let's say BICEP actually improves by 1 billion times, there's no dust, there's nothing, there's no way to prove it because you could always say inflation occurred, but it was too weak to detect the signal in a cosmic microwave background experiment. And that could go on forever. Whereas Steinhardt's model, along with other collaborators, proposes that the universe didn't have a Big Bang. It didn't have a singularity. And it has a lot of really nice features. I ask you, have you ever thought about, let's say the Big Bang is correct, and most of, I believe that in the Big Bang, up to a point, although as my friend and your friend Sean Carroll points out, if you go back in time, the Big Bang is really the beginning of our ignorance. In other words, going back in time, we don't know much more about what happened beyond the first 3 minutes after this origin of the elements.
Yeah, I mean, I think it's super important that I don't think there's anyone disputes this idea that the universe is expanding today, and that if you ran the clock backward, the universe would be closer together in the past. Yes. And you get to a certain point, as you said, 3 minutes, a nanosecond after the Big Bang itself, and then you run into problems. And the Big Bang is really just describing from the point where you have no problems forward in time. It's that, it's whatever comes before the Big Bang is the part that is still very complicated because it would lead to different things. So I don't think it's fair to say that anybody, if people dispute the Big Bang, then that would be disputing that the universe itself is expanding all around us, which is a
Right. So yeah.
weird
So
thing to dispute.
yeah, that would be like being an anti-vaccinator,
Yeah,
working for the
yeah,
CDC or something, right? So there's that, right? No, you're absolutely right. But the question of could there be an alternative cosmogenesis event that doesn't feature a singularity, a singular origin of the universe, that gives many people, including me and including many working cosmologists, some pause. Because think about it, to my knowledge, there's no example of something infinite that we can measure that then transitioned and tapered into something that is finite. We don't have an example of that where you have something with infinite temperature, say, and it cooled off. And, it's sort of like Zeno's paradox. I always say, like, if you think about it, you had to start, let's say at one point, if it's now 3 degrees Kelvin, let's say it started at infinite temperature, it had to go through a phase when it was infinity minus 1 Kelvin, right? Infinity minus 2 Kelvin. And so where does that get you? The question of how you can transition. There are no examples of that in physics. It doesn't mean it's wrong and that there wasn't a singularity. It just means we have to understand it. And I think the most honest answer to those questions at this moment is we don't know. The title of one of my friends, Jorge Cham and Daniel Weitzman's book, we don't know.
yeah,
We have no idea.
yeah. We don't know. Let's find out. But the thing is like, either the universe has always been, or the universe started itself, or the universe was started. Either of those is a mind-bending concept. None of them is, none of them goes down easy. And yet it has to be one of them. And so, the search continues. And
yeah, what's so exciting is that this model that he proposed is called the bouncing model. This has a couple of features. First of all, it doesn't have a Big Bang. It doesn't have a single start point for the universe. It's cyclic. It goes through an potentially infinite series of collapses and expansions. And that kind of harkens back to the good old days of Aristotle and beyond, where the universe was infinite. It's not infinite static the way that many people thought it was. It's infinite and dynamic, but the time scale that it changes over is minute. You cannot detect, could be trillions of years for the collapse process, for the expansion process. It also does not feature this multiverse, this problem of, according to Paul Steinhardt, that you can basically get any result you want, and therefore a theory doesn't have any predictive ability to do that. If you say you could either be left-handed or right-handed or ambidextrous, okay, it's right, but it doesn't provide you any surprise. It doesn't provide you any information content.
Yeah.
And so it has other issues that it also has to require this mysterious fluid called a quantum field. It may need multiple quantum fields, but in essence, it avoids these messy problems of quantum gravity. We don't need a quantum gravitational period because the universe never collapses down to the scale below anywhere close to the Planck scale, where you would need a quantum theory of gravity, which has proved completely elusive, the theory of everything, for generations of young physicists have kind of gone down that rabbit hole for decades.
Yeah, well, I mean, it's, the universe doesn't need to make sense to us, and there have been plenty of situations where what the universe came up with was a complete and total surprise and absolutely defied our expectations and our understanding. I mean, just look at quantum mechanics as a science that is utterly baffling and yet, predictive like no other theory science has ever come up with.
That's right.
We've got a bunch of questions from the audience that I would love to dig into, but also you had a colleague die just in the last couple of weeks. So I know you wanted to say a few words before we move on.
Yeah, I wanted to just pay homage to my late colleague, Margaret Burbidge, who passed away yesterday in her home in Northern California. And Margaret was one of the founders of the Center for Astrophysics and Space Sciences that I inhabit at UCSD. There really was no such place before she came to San Diego. And she was really only brought here because of a series of fortunate events that began with her not being able to use telescopes on mountaintops in California, and prior to that, not being allowed to be the astronomer royal in her homeland of England. She was the chief astronomer at the Royal Greenwich Observatory. And for every generation of astronomers that had such a position, going back hundreds of years, whoever held the position of the director of the Royal Greenwich Observatory, only he, was also what's called the Astronomer Royal, which is currently held by Martin Rees. Lord Martin Rees today is a friend of mine. And Lord Martin Rees always jokes with me that his main job is not to tell the Queen her horoscope, but to do many other important duties. But Margaret was passed over for that. And she was the first woman, and to date the only woman, to hold that role. And she really deserved to have those accolades. But thankfully, my colleagues in the UK were chauvinist pigs, and they wouldn't let her do it, because without that, maybe she would never have ended up here in San Diego to brighten up my life. So you never know. As I say at the end of the book, as Soren Kierkegaard said, life must be lived forwards, but can only be understood backwards. And so one of the properties of the human mind is to kind of confirm things, right? So here's a picture of Margaret in the book. This was taken by Ansel Adams, the famous wildlife photographer. These are some of the only pictures that I know that he ever took of a subject indoors, and it's just quite stunning. So if you get the book, they're in there. So she passed away yesterday at the ripe old age of 100. She turned 100 on August 12th, which is usually the peak of the Perseid meteor shower. And what Margaret did was really help to understand the process by which elements heavier than hydrogen and helium get formed in the universe. And she showed that these very heavy elements like iron, silicon, et cetera, that they get formed in nuclear processes that occur inside of stars. And she did this with her husband and also with two Titanic physicists, one by the name of Willie Fowler, who won the Nobel Prize in the 80s, and another by the name of Fred Hoyle, who never won the Nobel Prize and is best known for, he was an amazing astronomer, but he's best known for being the foremost advocate for the steady state theory.
Right.
And actually,
he came
Margaret's
up with the
husband,
name
Jeff,
for the Big Bang, right?
Yes, he coined the name Big Bang.
Yeah.
He coined it allegedly as a pejorative, for something we won't get into because you've got young listeners out there. But it's something that shouldn't be said in a rated G audience. So Margaret, when she came here, she also took under her wing a young astronomer by the name of Vera Rubin. And Vera, of course, went on to provide the most definitive evidence for the existence of dark matter. And that was done in, I promise that female astronomers don't always use microscopes, but the two pictures I have of them, they're both using microscopes. So they both were here in the early 60s, and Margaret really helped Vera and took her under her wing to teach her how to use optical telescopes to measure the properties of these spiral galaxies, which would then later be used by Vera to determine that the fall off of the rotation curve of galaxies was simply too shallow to be explained. She was the original flatten the curve advocate, because she measured these rotation curves that were exquisitely flat out to, hundreds of galactic core radii from the center of all these spiral galaxies. And the inevitable conclusion astronomers were led to is that there must be some invisible form of matter, much greater in amount than the perceived amount of luminous matter. So Margaret, yes, she passed away. She did live a wonderful, rich life. She has many things named after her. We have a professorship named after her, an honorary professorship named after her, which is currently held by a friend of mine, Elena April, who's the director, and you should get her on the show someday. She's the director of the Xenon experiment that's looking for dark matter.
Right, yeah, of course.
Looking for dark matter.
Yeah.
So she's here. She's a direct influence on that. And I have some interviews with people. I want to encourage people to tune into my YouTube channel, which is just Dr. Brian Keating. And that YouTube channel, I've got interviews with her, and I have a video tribute to Margaret that we made on the occasion of her 100th birthday. So I hope that people will tune in and pay a little bit of homage to this woman who helped us understand how the very dust of the universe gets into our veins, namely the iron that's produced in stars, gets into the hemoglobin molecule in our blood. And thus, as Carl Sagan said, we have star stuff flowing through our veins, which is absolutely accurate.
Yeah, yeah. What a legend. And I mean, that same story comes up so many times. So many fantastic female astronomers made a gigantic difference. And you wonder how many could have made more of a difference if they had more opportunities given to them. If they had to even just the same number of opportunities given to them as their male colleagues.
Yes.
So we've got a couple, like I said, I've got a couple of questions here that have come in from people who are watching. let's see. So Southern scientist asks, do you think it's possible that we could prevent the universe's death in a few trillion years? So if this bouncing model is the way this works, how does that play out, and can we stop it? Because
Yeah.
I'm expecting that bouncing universe doesn't really have a lot of room for us in it.
That's right. I was reminded, I was talking to on my podcast for Into the Impossible, we call it, which I recommend folks tune into. I interviewed Michael Shermer, the famous skeptic, on Friday, and that interview is going to air hopefully tomorrow. And in it, he recounts in one of the chapters of his book, which is called "Giving the Devil His Due," he recounts the story from Annie Hall, which, if you remember this film by Woody Allen, who's currently in cancellation quarantine for good reason. But but anyway, he recounts as a young boy, Alvy is his name. He says, he goes to a therapist. His mother brings him to a therapist and says, my son refuses to do his homework. The therapist asks Alvy, Woody Allen's younger version. He says, "Why don't you do your homework?" He goes, "Well, I found out that the universe is expanding, and eventually it'll just rip apart, and nothing will be left at all of our entire existence. So existence is futile." And his mother says, "What does that have to do with anything, Alvy? Brooklyn's not expanding, and you're in Brooklyn." And so yes, the universe is going to either take on one of several different fates. One of which is the slow expansion, cooling, so-called heat death of the universe. Everything evaporates away over the course of trillions of years. Other things that could happen, the universe could lose its dark energy. Its dark energy could actually decay away. We have no reason to suspect that couldn't happen. And as quantum physicists have said for generations, that which is not forbidden is mandatory. So that could happen, leading to the runaway contraction of the universe and annihilation of it into photons and neutrinos and things like that. Or if Paul Steinhardt's right, there could be this other type of field which slowly decays and changes, leading to a collapse that doesn't become a singularity. But in all those cases, the timescales we're talking about are tens to hundreds of times longer than the current age of the universe. So you're talking about hundreds of billions of years, perhaps trillions of years. So keep paying your taxes out there.
Yeah. Brooklyn isn't expanding. There was a sort of a thought experiment from Sean Carroll that I liked, that if you sort of run the math long enough, you'll get a time where just through quantum effect, the entire universe will rearrange itself into a Big Bang. You just have to wait long enough for that event to occur. So, you might have another way to go about it. So then, do you think that, that we will ever gain mastery over the universe at that fundamental level? Things like entropy. These, when you learn about entropy, it freaks you out for these exact same reasons. You sort of have this existential thought about, the future, and there's no way to prevent entropy. Could we ever prevent entropy?
Well, yeah. So this is the kind of reputed rumor, perhaps, that the U.S. Patent Office gets several patents every day about a perpetual motion machine. So there are certain laws of physics that seem to suggest that, according to these laws of physics, that there's no such thing as a free lunch. And you can't even try, because entropy has to be found to increase, at least on a macroscopic scale. And that might be a good thing, right? Because according to people like Sean and others, that might be intimately related to the flow of time in one direction, that there could be an arrow of time, as one of his books talks about. On the other hand, can you reduce time locally, or can you reduce entropy locally? Yes, of course. That's how you can transfer entropy and cool off a drink of, fine vodka over here, or whatever your favorite drink is up there in the Labatt's, or whatever you drink up there. I don't know. But yeah, you could do this. You could potentially do it on a local scale. Now the question is, can you reverse time locally? That's a much harder question to answer. We know that if I just showed you a pendulum and it's moving back and forth, you can't tell me if time is going backwards or forwards in that illustration. Similarly, if I show you the solar system, from the solar system northern hemisphere, if I look down the hemisphere, you'll see planets going in one direction. But if you went underneath it and looked up, it would look like it's going counterclockwise. Now, that means the macroscopic laws of physics don't have an arrow of time. You can just reverse the direction, velocity, and reverse time, and you get the exact same behavior. So the question is time like that? According to Einstein, space and time are just two different aspects of the same coin. And so, some people have gotten into this. I personally don't believe that there's a way, at least, to do it on a scale that would be meaningful. My late great colleague Freeman Dyson, we also interview on my YouTube channel. My
We'll put a link. We'll put a link in the show notes.
Yeah,
for sure. Yeah,
got to do it. Awesome, great. Yes, as I said, I'm trying to get the logarithm.
Yeah, no, I know you'll make it.
So when we do the math according to Freeman, it's possible to characterize certain civilizations according to how much energy they harvest, the Kardashev scale, et cetera. And he came up with this idea for Dyson spheres. But I asked him, do you believe in these Dyson? Do you believe they're out there? And he's like, well, nature has more imagination than we do, so it's impossible for us to really forbid that from happening. On the same way, we can't really think about trapping the energy of the expanding universe within our solar system, within our galaxy, because it's not relevant. It's not occurring within our galaxy. So you're talking about processes that play out over the span of light years. For me, it's impossible, but I'm happy to be proven wrong. In fact, if I am proven wrong that you can reverse it, I'm willing to pay out $100 in the current value of that cash whenever that's actually
right.
Whenever that actually happens.
Well, that's like a can't lose bet, because then you also get all the benefits of reversing entropy and.
Yeah, exactly. I'd be glad to do that.
Yeah, exactly. So let's see. Larry Beckham asks, do you know about the Wheeler-1 electron theory? Are you familiar with that?
I do not.
No? Okay.
No. If it's John Archibald Wheeler, I could probably...
It's funny. There's been a whole bunch of, I guess, alternative cosmological ideas from various people that a bunch of the viewers are quite excited about. And they are sort of hoping that I will be bringing on the expert who can speak about these. But I know that, it's sort of, everyone's got their wheelhouse, right? And they're so focused on the science that you're working on, and and it's like it's impossible to be able to know at a level that you can actually articulate it, to give them credit, to give what they're trying to propose a level of credit. So
right.
So Arjone asks, how could the universe crunch down to its previous size without forming a singularity? Would black holes form before it gets back to the size of a grapefruit?
That's a very good question. So according to this model of Paul Steinhardt, his colleague in Aegis, and Neil Turok at Perimeter Institute, that there is a separate sort of scalar field, not unlike the inflaton that causes the universe to expand, and that the universe can actually contract and perform what's called a classical bounce. So a quantum bounce would mean that, yes, you have to transition down to the size of a sub-Planck scale, or possibly slightly comparable Planck scale. In their model, you never make it to that level of density. Therefore, quantum effects are not really relevant. Quantum gravitational effects are not relevant. There are quantum effects if the universe actually contracts or is associated with an energy scale. In this case, it's 10 to the 16, 10 to the 15 giga electron volts, and that can be related to the Planck scale. And so it depends on the maximum expansion that the universe undergoes. And it's not like the classical intuition of like throwing a ball up in space and a gravitational field will come down in vacuum at the same exact velocity. So therefore, you'd think naively it would collapse to a point. In their model, there are relativistic effects, classical general relativistic effects, that don't require that to occur. So it actually doesn't have to form even a black hole.
Right. And that idea of, it's sort of like the same question of why didn't the universe itself just form into a black hole instantly after it formed? And
that's right.
And, my understanding of the answer to that is just that you need a difference in density. And if you've got that smooth density across the entire universe, then you're not going to get that compression in any one local area. And
that's right. It's like percolation, right? You need to have some broken symmetry, it's called, exactly.
Right. And so you would expect, as the whole universe is coming back down together again, you're going to be in that similar symmetry as it's all coming together.
Yeah, it is very sophisticated, kind of mathematical tour de force, and it's evolving over time. I'm not such, necessarily a proponent of it as in the general idea. that more than one theory should prevail. In other words, you should have a couple of different options, and there should be a marketplace of ideals. If you can't if you have only a monopoly on scientific thinking, I think it leads to really stilted growth. And I know, that's uncomfortable and popular to say sometimes, but I do think it's healthier when we have multiple flowers blooming in the theoretical landscape for experimentalists like myself to target that, as long as they make crisp predictions that can be refuted.
It's a similar situation to what's happening in the world of particle physics, right? I mean, the Large Hadron Collider has reached it did its job, and now what comes next, right? And so there have been all of these alternative theories or extensions to the standard model that have been proposed, and the Hadron Collider has searched, and none of it have turned up. And if there had been more alternative theories in the pipeline, then you could be using this time maybe more productively to be able to try and search for some of the ramifications of these ideas. And because everything was resting on supersymmetry, now these conversations of, okay, like, what else have we got, are starting now, as opposed to 20 years ago when they should have been started.
And you have a generation of young physicists trained to use a tool that, it might be, time to propose the next tool. But the problem with these they're kind of victims of their success, in that, it's exponentially more difficult, more expensive to build these accelerators. And there's sort of an upper limit to, kind of GDP and size and collaboration. I talk about that in the book, how it really, after the beginning of the end of World War II, when so much energy and money went into physics and nuclear physics, that's really when these colliders and nuclear particle accelerators really took off. And as a side benefit, there was the development of radar, which led to the microwave antennas that we use in the CMB field. And in fact, the CMB was discovered at Bell Labs, which was, have been working on telephonic communication using radar that had been developed itself in World War II. So maybe one of the outcomes of, this awful coronavirus pandemic on the good side will be, there'll be kind of a Manhattan Project in biology and physics, biophysics, to understand how we can conquer these things using worldwide collaboration. And maybe there won't be the same appetite for building huge accelerators, but there'll be bioaccelerators, understanding drug development, using the laws and data processing and data science that we physicists really pioneered.
Yeah, we are absolutely seeing this. It is pretty stunning to see the number of research papers that are coming out to try and understand COVID and SARS-2, and attacking it at every step of the way, in terms of treatment, in terms of vaccines, in terms of prevention, in terms of decreasing the sort of the epidemic side of things, the spread, societal changes, and even just like the way we get groceries. Like literally everything is happening. Everything is changing right now because we're forced to. People are talking about toilets that may be able to detect various viral loads in your body as you go to the bathroom every day, to sort of catch. People are talking about how people are wearing there's internet connected thermometers that are tracing the level. Here. Oh, do you have one? Okay.
Aura rings. I just got it. I can't tell if it works, or I bought a $200 piece of
So they're tracing people's fevers, and they're detecting where fevers are spiking and so what if we have a sort of worldwide change in the way surfaces are considered? Like, what if doorknobs we make them out of copper, or we make them in other kinds of materials that don't transmit diseases in the same way? So you're seeing, and it is a war, and it is the same level of ingenuity to being applied at a common enemy that has never existed in this field before, because times are desperate. And and it's that mentality that is wonderful to see, and you wish it could be applied across other fields as well. And
I'll just give you a teaser. One of my two of my colleagues, David Spergel of Flatiron Institute and Princeton University, and Katie Fries of University of Texas at Austin, they had a paper that used kind of DNA as the dark matter detector. So using like types of gel electrophoresis and and the growth patterns of DNA, and looking for mutations as a sign for when DNA had interacted with
Wow.
this
With dark
nucleic
matter.
acid. It's just, yeah. So
That's
I mean,
interesting.
look,
Yeah.
that's a long way off,
Who
but
knows?
look at the creativity.
Yeah.
Yeah, it's
Yeah, I love it.
really cool, right?
Yeah, we've reached the end of our hour, Brian. So let's talk about one, show off the book again, just so people
Okay.
know
Yep.
that you've got a book, and of course,
Losing the Nobel
yeah.
Prize.
So for people
Just
want to chase the Nobel Prize, Brian's got some advice for you. And of course, you are doing, as you said, you've got your own podcast, your own YouTube channel here. We'll put a link in the show notes and all of the places. But what is the format? You've got interviews on a regular basis?
Yeah, so I've had the pleasure of interviewing everyone, as I said, from from Freeman Dyson to interviews with people that knew Margaret and myself, as well as folks from Roger Penrose. I've had on four
Wonderful.
times, I think.
Yeah.
And we try to get greatest thinkers, authors. Michael Shermer was on, as I said last week. His interview's up. Peter Diamandis is coming on.
Great.
Mario Livio, who
Yeah.
I'll connect you to if you don't know.
Yep.
And we've got about Neil Shubin, who's an evolutionary biologist at Chicago. So we try to get the brightest minds, engage them in a single question, which revolves around how can curiosity, imagination, and forethought, how can those be inculcated and taught to our students and people who are just generally curious about how the universe works.
Fantastic. Well, Brian, always a pleasure to hang out and chat with you, and I'm sure we'll be talking again in the future. And good luck with everything you're doing. I'm sure you will overtake me on this logarithmic curve. So, all right.
Got to have someone to look up for.
There you go.
Or what's a heaven for?
Yeah. All right.
Bye,
Take
Fraser.
care, man.
Thank you so
all right.
much.
We'll see you next time. Oh, and everyone who's watching, you notice there's a second episode that's going to be starting in an hour, and that's with Scott Manley. That was the time that Scott could do this, so we're going to have a weird double feature tonight. So first Brian, then we've got Scott Manley. So come back in an hour, and we'll hang out again. All right, thanks, Brian.
Thanks so much.
End the stream.